From coastal defenses to complex pipelines, masterful construction and elite welding techniques shape resilient infrastructure against nature and time itself. The stone extraction process at the quarry is carried out through a well-organized, multi-phase operation designed for efficiency, product quality, and safety. The process begins with blasting preparation. A trained blaster carefully lays out a blasting pattern, ensuring that the correct amount of explosive force is assigned to each hole. This precise layout creates safe blasts while minimizing ground vibration. A subcontracted drilling company then drills approximately 50 holes, each about 5.5 inches in diameter, a task that typically takes 2 days. Once drilled, the holes are loaded with explosives and connected using electronic blasting caps. These caps allow millisecond delays between individual shots, which significantly reduces vibration and improves blast stability. After blasting, the operation moves into loading and hauling. Broken rock from the muck pile is loaded into 2 60-ton haul trucks using either a Cat 988F front-end loader or a Volvo 460 tracked excavator. The haul trucks transport the material approximately 500 feet to the primary crushing station. The next phase is crushing and screening. At the primary crusher, trucks dump the rock into a hopper where a grizzly feeder pre-screens the material. Only rock larger than 5 inches enters the 42x48 jaw crusher, which reduces it from large boulders down to 8 to 12 inches. The crushed rock is conveyed out of the pit to a surge pile, allowing continuous and efficient plant operation. From there, material is fed through scaling screens, cone crushers, and sizing screens. Larger material is sent to secondary and tertiary crushers, while smaller material proceeds to the wash plant, where fines are removed and aggregates are separated into final product sizes. The final phase involves customer loading and ticketing. Customers are directed to designated stockpiles, where a Volvo 220 front-end loader loads the material. Typically, 3 scoops fill a 23-ton truck. Each vehicle then passes over truck scales and receives a printed ticket. Throughout all phases, safety and environmental control remain a priority. The quarry emphasizes injury prevention, dust suppression, using recycled rainwater, and has proudly achieved 10 years without a workplace injury. The pile driving process is carried out at the south abutment of Bridge File 76077 using a heavy pile driving machine. First, the pile sections are carefully positioned in their designed locations and held vertically by the pile driver's leads to ensure proper alignment. Once in place, the hammer begins delivering repeated blows to drive the pile into the ground. During the operation, the progress of the pile is continuously monitored. To determine whether the pile has reached its required design strength, engineers apply a calculation formula that takes into account the energy output of the pile driver. This formula relates the hammer energy to the penetration achieved with each blow. The pile is considered finished when the penetration per hammer blow is reduced to the specified value, indicating that sufficient bearing capacity has been achieved in the soil. In this case, the first pile sections did not reach the required bearing layer. Instead, they were driven fully into the ground without meeting the target resistance. As a result, the operation continues by adding another pile section. A new section is spliced onto the top of the installed pile, typically by welding, to extend its length. The pile driving then resumes until the pile reaches the design depth and bearing capacity required for the bridge abutment. Concrete pouring begins by placing the fresh mix continuously along the length of the seawall, following the prepared formwork. Mixer trucks discharge concrete in a controlled sequence to maintain a steady flow and consistent quality throughout the pour. The operation proceeds section by section to avoid interruptions, ensuring that the concrete remains workable and that cold joints are minimized along the cap. As the concrete is placed, workers immediately consolidate it using internal and surface vibrators. Vibration allows the mix to settle evenly within the formwork, fully encapsulating the reinforcing steel and eliminating trapped air pockets. This step is essential for achieving a dense, durable concrete structure capable of resisting wave impact and long-term environmental exposure. Care is taken not to over-vibrate, which could cause segregation of the aggregate or weaken the finished surface. Once the formwork is filled to the required height, the concrete surface is leveled using screeds and straight edges that run along the top of the forms. This process ensures uniform elevation and proper alignment along the entire seawall. Any excess material is removed and low spots are filled immediately to maintain continuity and structural consistency. After leveling, finishing crews refine the surface using hand tools. The concrete is smoothed to achieve an even texture, while maintaining the designed slope that allows water to drain away from the seawall. Edges are carefully shaped and compacted to reduce the risk of chipping and to improve the durability of the exposed corners. Particular attention is given to transitions between sections so that the cap appears continuous and uniform once completed. As the concrete begins to set, final finishing passes are made to correct minor imperfections and ensure a clean surface profile. Timing is critical at this stage, as finishing must be completed before the concrete hardens too much, yet not too early, to avoid surface defects. The goal is to produce a strong, well-bonded cap with a neat and professional appearance. Following finishing, curing measures are applied to protect the fresh concrete. The surface is kept moist using curing compounds or water to prevent rapid moisture loss. Proper curing allows the concrete to gain strength gradually, reducing shrinkage cracking and improving long-term performance. This is especially important in a marine environment where temperature changes, wind, and moisture can affect early-age concrete. Once curing has progressed sufficiently, the formwork is removed. The exposed concrete cap is inspected to confirm alignment, surface quality, and structural integrity. The finished cap forms a continuous protective element along the seawall, enhancing resistance to wave action and erosion while providing a durable and stable top structure for long-term coastal protection. The upgrade works at Hume Dam represent one of the most significant dam safety improvement projects ever undertaken in Australia. Central to this upgrade is the construction of a massive 50,000-ton concrete stability wall, designed to strengthen the dam and ensure its long-term safety under extreme flood and seismic conditions. The time-lapse footage clearly captures the complexity, scale, and precision involved in building this critical structure. The construction process begins with extensive site preparation at the downstream face of the dam. Temporary access roads, working platforms, and safety systems are installed to allow heavy machinery and construction crews to operate efficiently. Excavation works follow, removing soil and rock to reach a stable foundation. This step is essential, as the new concrete wall must be firmly anchored to withstand enormous hydraulic forces exerted by the reservoir. Once excavation is completed, foundation treatment is carried out. The exposed rock surface is carefully cleaned and strengthened, often using grouting techniques to seal cracks and improve load-bearing capacity. This ensures a strong bond between the existing dam structure and the new concrete wall. Surveying and alignment checks are performed continuously to guarantee that every element is built according to strict engineering tolerances. The construction of the stability wall then proceeds in stages. Formwork is installed section by section, creating molds for the concrete pours. High-quality reinforced concrete is delivered to the site and placed in carefully controlled layers. Each pour is planned to manage heat generation, prevent cracking, and maintain uniform strength throughout the structure. Vibrators are used to compact the concrete, eliminating air pockets and ensuring dense, durable material. As the wall gradually rises, reinforcement steel is installed to enhance structural performance. The time-lapse video highlights the repetitive yet highly coordinated nature of the work, with cranes, concrete pumps, and crews operating in a tightly controlled sequence. Curing processes are applied after each pour, allowing the concrete to achieve its design strength before the next stage begins. Throughout the project, strict quality control and safety measures are maintained. Continuous monitoring, testing of concrete samples, and inspections ensure compliance with engineering standards. Despite challenging weather conditions and the sheer scale of the structure, the construction progresses steadily. Upon completion, the 50,000-ton concrete wall significantly increases the stability of Hume Dam, improving its ability to withstand extreme events. This upgrade not only extends the operational life of the dam, but also enhances protection for downstream communities. The project stands as a powerful example of modern civil engineering, combining careful planning, advanced construction techniques, and long-term infrastructure resilience. The Port of Durban experiences a busy morning as multiple vessels enter and depart under the coordination of Transnet National Ports Authority and Transnet Port Terminals. A port helicopter is actively deployed, dropping off and collecting harbor pilots as they attend to vessel after vessel. Container ships such as HSL Parity and MSC Mariana depart, while MSC Maureen and the Supermax MV Corona arrive. Several other vessels remain at anchor, awaiting pilotage and port services. The viewers witness the dramatic moments when massive ships approach the coastline or harbor and unexpectedly lose control. These vessels, weighing tens of thousands of tons, move slowly but carry enormous momentum, making any mistake during docking extremely dangerous. As the ships near the shore, strong winds, waves, or powerful currents begin to affect their stability. In some cases, sudden mechanical failures or delayed engine responses prevent the crew from reducing speed in time. Even a small miscalculation can cause the bow of the ship to drift off course, pushing the vessel directly toward the shore or harbor structures.
Aynen bu şekilde gelsin. Kıvırsın yani. Böyle iyi Mahmut, böyle iyi. Ne ettik ki la bu?
Harbor pilots and crew members work urgently to regain control, using engines, rudders, and tugboats to correct the ship's direction. However, due to the ship's immense size, these corrective actions are not always effective. The vessels may scrape along the quay, collide with breakwaters, or run aground on shallow coastal areas. The tug Umbilo is a robust harbor vessel designed to assist large ships like the Falcon Trader as they navigate tight waterways. Built in 2017, Umbilo measures about 32 meters in length and is equipped with powerful propulsion systems that give it excellent maneuverability and pulling strength. In the video, Umbilo can be seen steadily guiding Falcon Trader along the river, its engines producing steady thrust as it keeps the larger bulk carrier on course. Falcon Trader, a Panamanian-flagged dry bulk ship around 200 meters long, relies on Umbilo's precise control to avoid shallow banks and other river traffic. This kind of operation highlights the essential role tugboats play in safe navigation, especially when large vessels enter or leave ports and travel on narrow inland waterways. The operation is carried out on an in-service DN200 PE gas pipeline, where a DN110 branch must be created without interrupting gas supply. First, the pressure drilling equipment is assembled. Workers enter the excavation pit to conduct on-site inspection, precise measurement, and all preliminary preparations. The surface of the main pipeline at the drilling location is carefully cleaned to ensure proper installation and welding quality. During inspection, it is found that an operating water supply pipe is located about 1 meter horizontally from the gas main, which would interfere with normal drilling. The construction plan is adjusted on site by raising the branch pipe angle upward by 20 degrees to avoid the water line safely. Next, the fusion area of the saddle T fitting is marked. The surface is scraped to a depth of 0.1 to 0.2 millimeters. The fusion zone must be smooth and free from dents, scratches, or other defects, as proper scraping is a critical factor for successful welding. The saddle fitting is then strapped tightly, with the gap between the fitting and the pipe strictly controlled to be no more than 1 millimeter. An electrofusion welding machine scans the barcode and performs the welding of the saddle fitting. After that, the ball valve is welded in place. The cooling time for both weld joints must exceed 1 hour to ensure sufficient strength and stability. Once cooling is complete, the pressure drilling equipment is assembled and firmly fixed. The ball valve is opened, and the drilling cutter is advanced through the valve until it contacts the pipe wall. An air compressor is used to conduct a tightness test on the equipment, welded fittings, and valve to confirm there is no leakage and that all installations meet requirements. After passing inspection, drilling begins. The spindle is rotated for 2 turns, followed by manual feed of 1 to 2 millimeters, all in a clockwise direction. When the cutter fully penetrates the pipe, the feed mechanism is rotated counterclockwise, while the operating handle turns clockwise, retracting the tool to a travel of 70 to 80 millimeters. The spindle is unlocked, the cutter is fully withdrawn past the ball valve, and the valve is closed. Finally, the equipment is dismantled, completing the entire pressure drilling process. A metallic tapping saddle is first positioned and lowered into place beneath the existing pressurized pipeline. The surface area of the main pipe where drilling will occur is carefully cleaned, and a specialized industrial adhesive or sealing compound is applied evenly to the contact zone. This adhesive plays a crucial role in ensuring a tight, leak-proof interface between the pipe and the saddle once it is installed. The metallic tapping saddle is then mounted onto the main pipeline using a bolted connection method, typically with cast iron or heavy-duty fasteners. As the bolts are gradually tightened in a controlled sequence, the saddle clamps firmly around the pipe's circumference. This creates a rigid, sealed connection point designed to withstand internal pressure during the drilling operation. Proper alignment is verified to ensure that the future bore will be accurately positioned. Next, a shutoff valve of appropriate diameter is installed directly onto the tapping saddle. The valve selected must be a full-bore or full-port type, allowing the drilling tool to pass through unobstructed. The valve is securely fastened and sealed to the saddle, forming an extension of the pressurized system while still providing the ability to isolate the opening when required. Once the valve is installed, the entire saddle and valve assembly undergoes a pressure test. This test confirms that all seals, bolts, and interfaces are secure and that no leaks are present under operating pressure. Any necessary adjustments are made before proceeding. After successful testing, a specialized pressure drilling machine is mounted onto the outlet side of the shutoff valve. The machine is firmly fixed in place to prevent movement during cutting. The drilling phase begins by fully opening the shutoff valve. This allows the drill bit to advance through the valve body until it reaches the external surface of the pressurized pipe. The drilling machine is then activated, and the cutting tool begins to bore a precise circular opening through the pipe wall. Throughout this operation, internal pressure remains contained within the system. A key component of the drilling tool is the central retaining mechanism, often referred to as U-wires or coupon catcher. As the drill completes the cut, this mechanism securely holds the removed section of pipe material, known as the coupon. Retaining the coupon is essential to prevent it from falling into the pipeline, where it could obstruct flow or damage downstream equipment. After the hole has been fully cut, the drilling tool is carefully retracted. The drill bit and the captured coupon are pulled back through the open valve and into the drilling machine housing. Once the cutting assembly is fully withdrawn, the shutoff valve is closed completely. Closing the valve immediately isolates the new opening and maintains full pressure within the main pipeline. With the valve closed, any residual pressure trapped inside the drilling machine is safely released. The drilling unit is then detached from the valve. At this stage, the pressurized tapping operation is complete, and a clean, sealed connection point has been successfully created. The system is now ready for the installation of a branch pipeline or additional fittings without interrupting service or depressurizing the main line. The process begins with thorough surface preparation at the selected tapping point on the pressurized pipeline. The outer surface of the pipe is carefully cleaned to remove dirt, grease, moisture, and any contaminants that could affect sealing or welding quality. For PE plastic pipes, an additional scraping step is mandatory. A dedicated scraping tool is used to remove the oxidized outer layer of the pipe. This scraping area is extended at least 5 centimeters beyond the contact zone of the saddle on all sides, ensuring optimal conditions for a reliable electrofusion weld. Once the surface is prepared, the Fox Fittings Electrofusion hot tapping saddle is positioned precisely on the marked location. The saddle is then mechanically secured using the FOXGRIPL clamping system. The clamps are tightened evenly to a controlled torque of approximately 150 Newton meters, guaranteeing uniform pressure between the saddle and the pipe surface. Proper alignment at this stage is critical to maintain sealing integrity during both welding and drilling. The electrofusion welding process follows. A calibrated electrofusion control unit is connected to the saddle's electrical terminals. Welding parameters such as fusion time and cooling time are either read directly from the product label or automatically detected by the welding machine. Electrical current is applied, heating the embedded resistance wires inside the saddle and fusing it permanently to the pipe wall. After welding, the joint is left undisturbed for the specified cooling period to allow the material to stabilize and achieve full mechanical strength. Before any drilling takes place, a pressure performance test is conducted. This inspection confirms that the electrofusion joint and sealing elements are leak-free and capable of withstanding the internal operating pressure of the pipeline. Only after a successful test is the hot tapping operation allowed to proceed. For the hot tapping stage, a full-bore gate valve is mounted onto the outlet of the saddle, creating an isolation barrier between the pressurized pipeline and the drilling equipment. A specialized hot tapping drilling machine is then installed on top of the valve. With the valve closed, the drilling unit is securely connected, ensuring a sealed working environment. The valve is opened, and the drill bit is advanced through the valve until it contacts the pipe wall. Drilling is carried out either manually or by powered operation, while internal pressure remains fully contained within the drilling assembly. The dedicated cutter is designed to retain the removed section of pipe wall, known as the coupon, preventing debris from entering the pipeline. After the cut is completed, the drill bit with the retained coupon is fully retracted back above the valve. The gate valve is then closed, isolating the newly created branch connection and completing the hot tapping process safely under pressure. The bypass line is first connected to the main pipeline, and flow is gradually introduced into the bypass. Technicians monitor the system closely as the line fills, allowing pressure to build steadily. This stage takes several minutes, during which all joints and connections are inspected for leaks. The pressure in the bypass is increased until it matches the mainline pressure, with a target of about 480 kilopascals, or roughly 500 pounds per square inch. Once pressures are equalized, sandwich valves at both ends are opened, allowing the double stopple train to be pushed into position. With the stopples fully set, the oil flow in the main pipeline is diverted into the bypass line. This isolates the section of pipe that will be modified and redirects the product above ground into new risers and a valve header assembly for the pump station. The next step is to remove the remaining bitumen blend from the isolated pipe section. A vacuum system extracts the product while nitrogen is injected to displace it. Because the vacuum truck cannot discharge at high pressure, it transfers the material to a pressure truck, which then pumps it back into the active mainline. After the line is cleared, the pipe surface is cleaned down to bare metal to eliminate any risk of electrical arcing during cutting. Drip pans are positioned, and precision cutting equipment is installed. The pipe is cut incrementally, advancing the cutter by extremely small amounts until a clean break is achieved. A vacuum is kept ready in case any residual product escapes when the pipe separates. The removed section is lifted away, and additional cuts are made to prepare for the risers. Bentonite clay is applied inside the pipe ends to seal them temporarily, allowing safe welding of caps. The new risers are then aligned, adjusted, and welded into place. Final checks confirm proper access, alignment, and integrity, completing the pipeline diversion and reconnection process. The process begins by cleaning the polyethylene pipe surface at the welding location. All dirt, mud, and contaminants are carefully removed to ensure a clean working area. The length of the Fox Electrofusion coupler is then measured, and half of this length is marked on each pipe end. These marks define both the scraping zone and the final insertion depth of the pipe inside the coupler. Next, the mandatory scraping step is carried out. A dedicated scraping tool is used to remove the oxidized outer layer of the PE pipe, typically to a depth of about 0.2 to 0.3 millimeters. This step exposes fresh material that is essential for proper molecular fusion. Once scraping is complete, the prepared pipe surface and the inner surface of the Fox coupler are cleaned using a lint-free cloth soaked with a specialized PE cleaning solution. After cleaning, the surfaces must not be touched by hand to avoid recontamination. The coupler is then slid onto the pipe ends according to the marked positions. Alignment clamps are installed to keep both pipes perfectly straight and to prevent mechanical stress during welding and cooling. Welding cables from the Electrofusion machine are connected to the coupler terminals. A barcode scanner reads the coupler code, allowing the machine to automatically set the correct voltage, welding time, and cooling time. The welding cycle is started, and the operator monitors the display to confirm stable power supply and error-free operation. Workers begin by preparing the pipe ends to ensure a clean and secure joint. A layer of specialized adhesive is carefully brushed onto the spigot end of the PVC tome pipe. This adhesive reduces friction during assembly and helps achieve a tight, reliable connection. Once the adhesive is evenly applied, the pipe ends are aligned and manually pushed together, allowing the joint to seat fully without the need for heavy machinery, even for diameters up to DN 315 millimeters. After the initial straight connection is completed, an Electrofusion 22.5 degrees fitting with a nominal diameter of DN 200 millimeters is installed. The fitting is positioned to match the designed pipeline direction, and the pipe is inserted into the fitting socket using steady, controlled force. The precision of the Electrofusion system ensures proper alignment and sealing, enabling fast installation under site conditions. Next, DN 200 millimeters pipes are installed in sequence. Each new pipe section follows the same procedure: adhesive application, careful alignment, and manual insertion into the previous joint or fitting. This repeatable process allows workers to extend the pipeline efficiently while maintaining consistent joint quality along the trench. Once a section of pipeline is assembled, backfilling begins. Gravel and crushed stone are poured into the excavation around the pipe. Workers distribute and level this granular material evenly along the sides and beneath the pipe to provide uniform support and to stabilize the alignment. The bedding layer is compacted as needed to prevent future settlement. Concrete is then poured into wooden formwork, placed at designated locations to create thrust blocks. These concrete supports are formed to resist axial forces generated by changes in direction or pressure within the pipeline. After the thrust blocks are completed, installation continues with the next pipe sections. The same sequence of pipe assembly, granular backfilling, and structural support is repeated progressively until the pipeline run is completed. Steel wire rope production is a highly controlled industrial process designed to deliver strength, durability, and reliability for heavy-duty applications. Throughout manufacturing, strict testing and quality control are carried out before, during, and after production to ensure consistent performance. All processes comply with major international standards such as G, B, EN, GHOST, and API. High-quality steel wires are precisely combined through mixed wire rope and advanced stranding techniques to achieve optimal load capacity and flexibility. After inspection, finished wire ropes are packaged according to Julie standards, using wooden or steel wheel reels to ensure safe transportation and storage while maintaining product integrity